Hello guys, welcome back to John's Workshop, and in this video we're going to be doing workshop tips number 4, and mainly because the project that I've currently got ongoing, turning 2 perfectly good cooking utensils into something else, a musical instrument hopefully, is going to take slightly longer than I expected. So we're going to shoehorn this episode in based on a lot of questions and feedback that I got from my previous hints and tips video, which was around controlling your sizes, and we dug into carbide usage a little bit and the use of carbide inserts, sintered carbide inserts on a lathe for controlling fine diameters, taking very small depths of cut. So go back and look at that video if you've not seen it. I think it's very useful, and if you've got a lathe and you're aiming for finished cuts, go and check that one out because there's some useful tips in there. So in this video we're going to explore carbide in a little bit more depth, and largely some hints and tips on care, usage, handling, things like that. There's some common mistakes that I see being made on YouTube by, and you know, not through anybody's fault, it's just through probably lack of experience or lack of bad experience and people yet to go on that learning curve. So if I can save somebody a bit of money on having to replace carbide through silly mistakes, then that's all good. We're going to look at the nomenclature a little bit of carbide. So what do we mean by that? We're talking about, you know, you get a box of carbide inserts, there's a whole coding system which is, as far as I'm concerned, in my geography, is based on the ISO turning inserts sort of standards, and in America and the US they've got the ANSI, which is the American National Standards Institute, so they've got their own standards, which is all fractional, so it's going to be largely based around metric. What I'm not going to do is walk you through that entire spec. The spec is massive, it's huge, that's why lots of people find it confusing, but what I am going to do is just point towards what some of the categorizations mean, what they do, and try and demystify it a little bit, because it's not that complicated. You know, of all the systems that I've seen be put into place, it's actually quite logical when you dig into it, so we'll have a look at that and hopefully make that a bit less frightening for people. We're going to cover milling and turning because that's what most people are up to in their home shop one way or another, and we're going to do a little bit on quality versus cost, so the quality of the carbide versus the cost of it, so we'll touch on that. We're going to try and angle everything towards home shop use wherever I can to try and make it more relevant for people in a home shop. We're going to attack the big question, and bit of a spoiler alert, I'm not going to give you an answer, or I'll tell you that up front. Very topical question. It gets very controversial. Lots of people with lots of different opinions on whether you should be using carbide in a home shop or not, and so I'm going to give you my interpretation of that and my experience of that, and largely it's up to everybody to make their own minds up based on what they're doing. So we'll touch on that, and I'm not in any way trying to make out I'm an expert here, because I'm absolutely not. Never worked in a carbide manufacturing facility at all. However, I've visited quite a few of them over my years, and I've spent a lot of time with some of the big companies developing new tooling, different tooling strategies, things like that are going to work on aerospace components, some of the tougher materials. So quite an insight into how they go through their design processes, how they go through the manufacturing processes, what kind of controls they've got in place. So I'm going to try and use that industry experience and channel it again, like I said, towards the home shop, just to try and give a bit more, you know, demystify carbide a little bit, for want of a better word. So I'll join you all in a minute. We'll get the welding table out, we'll get some carbide out on top of it, and we'll start digging in and see what we find. Okay, so if you've made it this far, you obviously weren't looking for a video of a cat doing something stupid, or somebody falling over or running into something and hurting themselves. So this picture should be fairly familiar to most people that have got this far in the video. So I've kind of split milling and turning, albeit that's not strictly true. A lot of the indexable carbide inserts can also be used in milling machines, in face mills and various different, you know, slot mills and things like that. So these are kind of dual purpose. These are really strictly single purpose, although, you know, again, you could use something like this in a lathe. If you don't have a milling machine, you could chuck up the carbide end mill and use a milling axis on the center lathe on the cross slide for milling. So yeah, they are interchangeable, but largely milling and turning separate. So my previous tips video, please go and look at that if you want to know more about these sintered carbide inserts, to go into a little bit of detail about why they're blunt and why that's important in terms of trying to control finish diameters. Really important information for that on a lathe, so go and check out the balance cut video with the information that I've already spoken about and discussed in terms of those. So just a very quick sort of run over and a couple of tips. You know, again, if your carbide end mills come in one of these things, leave them in it. Don't be tempted to take them out and throw this bit away, because it's in one of these for a reason, and that's to protect it. And we're going to come on to care of carbide a bit later in the video. So you know, a few different things here, ranging from, you know, specialist form tools that have had a shape or a form ground on them, a multi-flute style end mill that's got, you know, more than the regular 2 or 4 flutes on it. And I'm not going to really go into the reasons for that, but because I could be here for all day talking about just those 2 things alone. To the, you know, the big, you know, this is a big chunky, probably 25mm solid carbide slot drill. So, you know, incredibly expensive. Raw materials just alone of that is probably 120 quid, I would think, before you've started grinding anything into it. So yeah, very expensive. Down to the other end of the spectrum, you know, how small can you actually grind carbide? And I don't think my camera's going to do this one justice, but I think this is about, from memory, it's a 2 flute and it's 0.68 of a mil, I think, something like that, nearly 0.7 of a mil diameter with a ball nose on it, 2 flutes. And then the other option is a brazed carbide mill, something like this. This has got a form on it, but yeah, you can see there's 2 inserts there brazed onto a shank. And so they're the kind of different milling types. And then turning types, you can see we've got various different styles of inserts, and I'm not going to go into all the different names again because I'm going to be here all day, but largely, you know, different turning inserts, big and small, with different geometries on them. There's kind of parting inserts that most of you will be familiar with and have seen, that slide into a parting blade for parting off. There's, you know, triangular shape, there's square shape, there's what are classed as rhombic shape, which are these. There are threading inserts for single point screw cutting, and yeah, as I said, various variations on a theme. And these are all, sorry, I think I just called those rhombic, ignore that, they're not rhombic, they're W style inserts. These are the rhombic ones, the ones that are trapezoidal in shape. So we're going to go into that in a bit more detail just shortly. So one thing you will notice is there's different colours. So if I get just these 2 boxes alone, you'll see there's gold and there's black now, or grey. Now these are raw uncoated carbide, these are coated carbide. So effectively the substrate of this is exactly the same as what you've got here, except it's had probably a titanium aluminium nitride coating, looking at that colour. But yeah, that could be wrong as well. But yeah, typically the gold colour is a titanium aluminium nitride. And then you'll also notice, if you look at the inserts themselves, there's a varied mix of kind of patterns on the top of the insert, and that is the chip breaker. So that's put into there to try and control the chip when you're cutting, and that's what that funny pattern is. And some have got them, some haven't. Some are more, you know, some more, yeah, still got a pattern on. These small ones, they've still got a ridge in there, which is still a chip breaker. And sometimes that chip breaker will alter the cutting angle of the insert edge from being a positive to a negative, depending on the material that these are designed to cut. So yeah, and you can see now very quickly within a couple of minutes there how this can all get quite confusing quite quickly. So what I'm probably going to do is just go into the nomenclature a little bit now, but try and simplify it a bit, because largely in the home workshop, and if you look at most machining videos, you'll either see one of these triangular ones being used, one of these rhombic ones being used, which is a CNMG, and we'll come on to the nomenclature of that shortly, and or one of these square ones being used. And that's largely 90% of everything you will see used in a home shop will be one of those three styles of insert. The W style insert are becoming more popular these days, and for very good reason, and I'll go into why that is just shortly. And also you'll see parting off inserts being used, which are a bit of a different thing, and I'm probably not going to cover those in this video. I'm just going to cover the basic turning ones. So with all of that being said, and having probably confused the hell out of you all, we're going to come to the board now, and I'm going to go into some of the nomenclature that covers these. So if you look on any one of these boxes and you look on the back, and this isn't the right box for these inserts, but you'll see a load of information on the back of the box, a load of numbers and letters, and this is where it can get confusing fairly quickly. So I'm just going to draw some stuff up on the board, and we'll come back and try and simplify some of this coding around these inserts for a start, and then we'll work through into some of the other points that we discussed at the start. So when I look at the back of one of these boxes, like I just showed you, there are a series of letters and numbers on the back, and this is where it starts to get a bit mystifying for some people. These are all different classes that denote what the insert is, and there are roughly 10 classes. There's actually more than 10, and they come from either the ISO classification system, which is the International Standards Organization, or the ANSI, which is the American National Standards Institute. So what I've done is kind of done a blend of both, because I know I've got viewers in both areas predominantly. So these are the main classifications that you will get. So they will denote the shape of the insert, the clearance angle that's on the insert, the tolerance class, because these inserts are indexable. The tolerance class is what level of accuracy you have when you index the insert in your tool. The type of the insert, the size of the insert, the thickness of the insert, the cutting edge condition, the edge prep that's been done on that cutting edge, whether it's left hand or right hand, and any facet size that there is on the cutting edge. And that is a blend of ANSI and ISO, and it depends where you look, you'll get different answers to this stuff. So what I'm going to do to try and simplify this for people who are in a home shop and this is really confusing, is I'm going to largely get rid of a load of this stuff, because a lot of this stuff you don't actually need to worry yourself too much about. We can probably get rid of that one, probably leave it at, you can probably get rid of, yeah, probably those ones. So we can rationalise that down to 7 or possibly even 6 really for the home shop, for the 2 or 3 or 4 inserts that most people use on a regular basis. So what I'm going to do now is I'm going to put one of the codes up on the board, and we're just going to dig into what that actually means in terms of some of the coding, just to try and give you an idea. And I could talk on this for hours and hours, it's a big topic, but as I said, I'm trying to simplify this as much as I can. So we're largely going to focus on the first 4 or 5 of these, which will probably get you by in a home shop, if I'm honest, without the need for all the other stuff at the bottom. So we're just going to come back in and demystify some of that a little bit if we can. So I've got one of the codes up there, not all of the code, just a bit of the code that I think is important to the home shop. So it's a box of these inserts, CNMG 120412, and that's the start of that code. It's a rhombic style insert, so it's the one that you see me using all the time on my turning tools. So it's a kind of diamond shape, and we're just going to run into some of the classifications. So there's 16 shapes in all. So the C denotes the shape, and it's very simple for a home shop. There's a load more, but I've just pulled out the main ones that people are going to use, and it's quite self-explanatory with the exception of the W one. So S for square, T for triangular, C, D, E, F, M and V are all rhombic, and all the differences is the difference in the angle of the trapezium of the shape. W is a trigon, that's the only one that kind of doesn't really work in terms of its name, and R is round, and yeah, it's not difficult to remember those with the exception of the W one, as I demonstrated at the start of the video because I couldn't remember it. The next letter in the series, N, is around the clearance angle. So again, these are all of the classes with the exception of one. There is another one that I've not included which is a bit of a special, but these are the standard ones. So A through to G, 3 degrees, 5, 7, 15, 20, 25 and 30, and then N at the end is 0 degrees. So if you look at C and MG already, you can see that for C we're talking a rhombic insert, and for N we're talking 0 degrees clearance. So this is how it works. Now these tables and charts are easily, readily available on loads of internet researches. So what I'm going to do now is just run into the M and the G and the 120412 bit very quickly to say what they are, but it's worth just pulling out on the N one because this is really important. If we look at N being 0 degrees, if I look at that insert again, there is absolutely zero clearance on that. If you looked at a piece of high-speed steel, you'd have a rake angle, a clearance angle on the front of the tool. There is no clearance on this, which means this tool, the tool holder that holds this insert, has a negative rake on it, which then produces the clearance. And the benefit of that is then you've got 4 edges to go at on the insert. Because there's no clearance ground into it, you can use all 4 corners. And if you've got another tool, you can actually use the other 4 corners as well that presents that corner to this. So these are really good value for money inserts. The W style, even more so, they're even more better value for insert because you get 6 edges out of one of those. So yeah, as a standard. So it's worth looking at the shapes. Obviously with a triangular insert, if it's TN, you've then got 6 edges of the inserts because it's again 0 degrees rake, so it's a negative approach, so you'll get 6 edges to that insert. And if you get a round insert, now they're really good, and you don't tend to see those used in a home shop a lot. Now I would really suggest it's worth investing in a round insert because you get as many edges as you can fit around the circumference of the insert. So if you've got a decent sized round insert, all you've got to do is undo it, index it a small piece and do it back up again. Really useful, good for cutting aluminium depending on the geometry of the insert, but yeah, they're good for roughing off stock quickly. The disadvantage of a round insert is if you want to take big deep cuts, you're obviously increasing your, because it's a round insert, you increase your engagement, and if you've got a machine that's not up to it from a spindle bearing perspective, you'll start to get vibration and chatter and things like that because you've got more length of engagement. But in terms of value for money, round inserts go a long way. You know, you can get a lot of turning out of a round insert. So that's a bit of that. We're just going to run on to the other bits and I'm going to briefly go through it, but as I say, I'm going to keep it fairly high level. Okay, so we're on to the next 2 of the first 4 codes. So the M is for the tolerance class, and what I'd suggest is just ignore that. So you'll know whether you've got a CNMG insert, an SNMG insert, a T style insert, whatever the previous insert you got, you'll know what that is. For the home shop, the tolerance class, really, unless you're getting really down to fine level stuff, it's quite confusing, and this is where people will get lost with this stuff. So this talks about drawing an inscribed circle inside your insert and then measuring the distance from the inside inscribed circle to the point on the cutting edge, and it just gets really, it can get really confusing unless you know you've been doing this stuff every day, day in and day out. So I would just largely ignore that unless you really need to dig into it. Just know what your first 4 letters are for the insert type that you want, and try not to get too lost in that. The next one is a little bit more important, and this is to do with how's the insert held in the tool. So, and again, there's a load of classes, there's 15 different classes on this, but again, if you actually look what's going on with here, they're just repeats of the same thing but with different geometry. So a straight plain insert with no hole in it, so that's going to be clamped into the tool with a top clamp sitting on top of the insert. Then you've got a single-sided insert that's got 2 cutting edges on it with no hole in it. Then you've got a double-sided insert, looks like a Christmas cracker, so you've got 4 cutting edges on that one but no hole in it. And then you go back to really largely your N shape again for A, so it's the same thing again with a hole in it. M is the same as R but with a hole in it. G is the same as F but with a hole in it. And those inserts sit onto a peg when you put them on the tool, which then pulls back and clamps it, and then some of them will have a top clamp that comes over the top as well, and so on. And then you get into countersunk holes in the inserts for different styles. Again, I'm not going to go into all the depths of that, but that's what that 4th letter is. And if you need to know more, go and look at some tables. There's loads of reference material out there, but that's what it stands for. So we've covered the shape, the clearance angle, the tolerance classification that I'd largely suggest you ignore, and the insert type from a clamping perspective. Then we get into the sizes, which are the actual physical size of the insert. So I'm just going to run quickly through those really quickly, and then I'm cutting it at that. I'm not going to go into any more depth. This is just to show you a bit of interpretation. If I was to go through all the different permutations, this video is going to be hours and hours long, and that's why people get put off by this stuff, but I'm trying to just show you the bits that are really important. Alright guys, I promise this is nearly at the end of how far I'm going with this. So interpreting the next 3 sets of figures, and I'm going to use the ISO here because the ANSI is quite much different and more complicated for me because it's all uses fractions of an inch. I'm familiar with the ISO system here. So the first 2 numbers are the size of the insert, and again this is where it starts to get heavy because it starts talking about the diameter of the inscribed circle for a square or a triangular or a round, or a hexagonal, pentagonal or trigon style insert. They can all have an inscribed circle in them. When we get to a rhombic or parallelogram style insert like this, it talks about the length of the actual flat side. So they're measured differently with these. It gets a bit heavy, so I'm just showing you what it is and how to interpret it. If you want to do any digging, and the size is quite important, you may have, the size is probably one of the most important things you need to figure out. If you've got no inserts to go off and no previous boxes with the numbers on, then you're going to have to figure that one out the hard way, unfortunately. But that's what it is, and that's how it's calculated. The thickness is straightforward. It's the thickness of the insert, doesn't need any explanation. And the last 2 sets of numbers is the cutting radius. So I've just drawn a triangular insert there to show you, but it's basically the rad that's on the corner. So for our C&MG insert that we've got on the top there, we've got 12 on it. That stands for 1.2 millimeters. So that's our insert. That's how to roughly dig into the coding, and apologies for that. I feel like I've done a bit of a poor job really, because I've done half a job. I've not gone into it in its full depth, but I'm just trying to show you that it's not that difficult when you break it down into the small chunks. It's not that difficult to interpret, so you shouldn't be afraid of it. There's plenty of information on the internet around this stuff. It's not difficult to figure it out, and the information that is on the internet is fairly easy to understand and read. It's not too difficult. So go and have a look at one of the big suppliers, the Sandviks, the Seacos, the Kennametals, one of the big suppliers. Their websites are really well laid out and really helpful to help interpret this stuff. My warning would be, if you're in Europe or the UK, or make sure you're picking the ISO system and not the ANSI system, because if you get the wrong one, it's going to get quite confusing, because there are some subtle differences between the American system and the rest of the world. So just make sure that you're clear, and I've probably got that wrong and insulted all my American viewers now by saying Americans and the rest of the world. Apologies for that, but you know what I mean. Just make sure you're referring to the right system. So that's enough science. We're going to get into brass tacks now with the rest of the video, as we start talking about care and protection and things like that, and tips and hints and things like that. So some basic care and hints and tips around carbide. Carbide is extremely brittle, and if it's ground like an end mill to a very sharp cutting edge, even more brittle. So if you've got a load of these things and you chuck them all in a box, you can guess what's going to happen. You're just going to damage them fairly quickly. So that's the first thing. So as I said earlier, if they've come in one of these, keep it in one of these. If they've come as an insert in one of these boxes, don't take them out and chuck them all over the bench or the top of your lathe. Keep them in the box. It's the best way to store them. And so a couple of things that I see people who are not used to working with carbide do on a fairly regular basis, and this is really important. So on a lathe, I'll see people using they'll bring a tool up to the part, and then they'll start turning the chuck round to get a touch off to try and do it real fine, and that's great. With high-speed steel you can do that. With carbide, as long as you're keeping your direction forward as though you're going to cut, you're okay. The minute you even stop the chuck, and if it goes slightly backwards and that cutting edge is in contact with the workpiece, you're just going to chip the insert. You're going to lift the top surface off it almost instantly and wreck your insert edge very quickly, and then you're going to need to turn it over and get onto a new edge. So easy to do. I see so many people doing it. Similarly, and I'm guilty of doing this as well, you've seen me do it on my videos, there is my tool on centre trick, and I'm going to get my 6-inch rule and wind it in up against the part and see whether my rule's pointing this way or that way to know whether my tool's on centre. That's one of the quickest ways that you're going to chip your insert. If your rule is trapped between the tool and the part, and then you lift your rule up this way, there's a very good chance you're going to lift the top of the insert off. It's so easy to do, so easy to damage these things. And to the same end, and probably even more often done, is on a milling machine. You'll see people bringing their tool in up against a workpiece, and they'll be manually turning the spindle around by hand, looking for a light touch off the edge of the workpiece, and they're doing this with the spindle like backwards and forwards. And what's going to happen is exactly the same thing. While you're going forwards into cut, it'll be fine. The minute you rotate the spindle backwards, if the cutter's touching the workpiece, you will chip the cutting edge, almost guaranteed every time. It's so easy to do, and these things aren't cheap. So really take good care of them and think about that backwards movement either on a milling cutter or on an insert. It's the quickest way to wreck your carbide. It's so easy to do, and people who are used to working with high-speed steel don't worry about it, and then they pick carbide up and turn something backwards, carbide's gone. Lots of money down the drain at that point, especially on an end mill. If it's an insert, you can turn it over and get some more life out of it. On an end mill, you chip the flute away at the corner, it's toast, unless you're going to regrind it or send it away for regrinding. So just be very careful with that. So I've drawn a bit of a chart here. So this is the quality versus cost, and I've actually changed, for the chart, I've actually changed it to be cost versus useful work, and that could be quality or it could be useful work. They're one and the same thing largely. And this is a very typical chart used in large industry for working out which quadrant things fit in to try and make things jump off the page quickly to be explainable. So there's quite a bit going on here, so I'll explain. So down here is zero cost, high cost, zero useful work, high useful work, and then I've put at the top there, so regulated industry at that top corner and very unregulated work in this bottom right hand corner. And that's so that regulation drives cost, it always does. So if you look at sort of aerospace and defence, they very much heavily regulated, so they will be getting, and I've seen this firsthand, and largely that's why I've got boxes and boxes of this stuff. They will use inserts till you can't even see they've been used, and they'll take them out and throw them away because they don't want to damage or risk damaging the substrate of the material because of the conditions and the operating environment and the risks of something happening. So incredibly high cost, incredibly low useful work for that cost in aerospace and defence. Mould and die, largely high cost and sort of middle of the range useful work, largely because of the kind of materials that they're cutting, very, very hard materials, so they don't get the life out of even good quality inserts. They're not going to get the life. If you look over on the right hand side, so medical, automotive, industries like that, they're going to be reasonably high cost. They're going to be buying good quality stuff, but they're going to drive the tooling a lot harder, so it'll be properly worn out when they get rid of it, so they're getting maximum value for high cost. Oil and gas is a bit more regulated, so they're going to get less useful work, and they won't be using the cheapest stuff. They'll be using sort of middle of the road kind of quality tooling. And then as you get down into the bottom, heavy engineering, probably going to be getting the most value bang for buck out of Carbide, so they're going to be using not the cheapest but in the cheaper range of tooling, and they're going to be sweating that tooling until it's absolutely knackered, because they're not regulated in any way. Similarly with jobbing shops, things like that. And then on the left hand side you've got training schools, colleges, universities. They're going to be buying the cheap stuff. You know, everybody's on a budget these days. They're not going to be buying super high-end tooling, and they're going to be getting very little useful work out of it, because they're going to get used for odd little projects, bits and bobs. They're not going to get worked hard, and neither do the machines they've got. So, and then right at the very bottom here I've got low cost manufacturing. So some of the sort of Asian, Indian manufacturing houses, they're going to be buying their own products in dirt cheap, and they're going to be sweating it to death. And that's why when you buy something from one of those countries and you look at the surface finish you've got on it, it's poor, because they're absolutely raking the life out of their tooling and running it really high. That's why they're cheap, you know, simple as that. So where in there does the home shop sit? And it's really difficult to pin it, if I'm honest. So I've kind of drawn a box at the side, because every home shop's different. You know, I look at mine and what I've got, I use a bit of it, but you know, because I can, because I've got a machine that's machines that are capable of driving it to get the benefit. You'll get other home shops that have got tiny little machines. You're just not going to get the value. You're not going to get any useful work out of that. So you're going to be down probably in this bottom corner. And then you've got, you know, there's guys with home shops that have got, you know, modern CNC machinery in it. So they're getting up to the, you wouldn't buy a, you know, 60, 70, 80,000 pound machine, 90, even more, you know, in some cases CNC machine, and then put the cheapest of the cheap tooling in, because guess what's going to happen? You're gonna it's not worth buying the machine. So it's all a bit of a balance really, depending on where you are. But certainly home shops are going to get lots of useful work out of their tooling. They're going to push it to get maximum life out, whatever the case. So they're going to be on this right hand side of the box. So I hope that's been helpful, just to try and give you, I guess, again, the benefit of my experience and the different places I've been and the industries I've been in and out. That's how I map it. This hasn't come out of a book or off the internet. This is me just doing a brain dump on the board from the knowledge I've got. It's probably not right, it's just my experience, and I'm sure there'll be people who've got a different opinion to that, and that's absolutely fine, but that's the way I see it. Fundamental question: what's the difference between Chinese carbide and the carbide that's being used up here in the highly regulated industry? It's basically the base material. So this will be micrograin carbide. It's much more expensive to produce, it's much more expensive to grind. The tolerances that they're going to work to are far tighter, so that pushes the price right up. The coatings and specialist coatings and geometries are going to be much different, much more specialist, and that's what gets the cost right up there. Down here it's not micrograin carbide, it will be much coarser grain carbide. When they sinter it, the accuracy of the sintering process won't be as controlled, therefore the repeatability of the insert when you turn it round won't be as good. And you know, it's all that kind of thing. The insert's probably more likely to break down quicker, it's more likely to chip quicker. If you started using the, you know, the Chinese stuff on some Inconels and Nimonics that you use in aerospace, it would be gone in seconds. It just would not stand it. But for mild steel, things like that in a home shop, it's a pretty good buy. You can't grumble at the price. So yeah, old English saying, it's horses for courses really. It's whatever works for you. But that's my take on cost versus quality on carbide, so I hope that's been helpful. So we'll finish with the million-dollar question. Should carbide be used in a home shop? Yes and no. I told you I wasn't going to give you an answer. The real answer is it depends. So if you're fortunate, I'm really fortunate, I've got a Harrison M300. It will drive carbide within the range that it's supposed to work properly. Before that I had a little Denford Viceroy lathe. It wouldn't. There was really no benefit to carbide. And again, if we look back to industry to try and help us answer this question, why do we use carbide anyway? Why was carbide invented? Largely because of exotic materials, production pressures, time, faster cutting rates, things like that. So if you're not achieving any of those aims or goals in a home shop, then carbide's probably not the right material. And if you'd asked that question 10-15 years ago, it would have been a flat no. Absolutely not, because carbide was very expensive and still is if you buy it from Europe, the Americas, you know, Australia, you know, manufactured, very, very expensive. It's only with the advent of Chinese carbide that's changed the whole dynamic. So you can now buy a carbide M mill today, or a box of carbide inserts, cheaper than you could buy a high-speed steel M mill 25 years ago, manufactured in the UK or in Europe or wherever else. So it has changed the whole dynamic. But you know, the question is, with a carbide M mill, if you want to try regrinding it once it's worn out on the end, you know, if you've got a tiny machine, you're only taking 10-15 thou depths of cut, you're very quickly going to wear out that bottom 15 thou of the M mill. It's very quickly going to become useless. If you've got no way of regrinding that in your home workshop, then there's probably not a lot of benefit, if I'm honest. You'd probably be better with high-speed steel, where you possibly can regrind it. So there's lots of factors that fit into that. And what I would say is, just consider whether you think you're getting value. And if you are working with smaller machines, do some back-to-back trials and just look at cost versus what you actually get. Are you actually getting the benefit? And decide based on your output. And if you can see clear benefit, then especially with today's cheaper carbide, then it's probably the right thing to be using in the home workshop. And if you can't see that benefit, then you're probably better off with high-speed steel, to be honest, or traditional cutting tools. So yeah, it's a balance. It really depends on lots of factors: your power source, your machine's age, how good it is, how tight it is. There's a whole load of factors in there that will dictate whether you're going to get value out of carbide or not. So there's no clear answer to that question, unfortunately. And on that note, I'm probably going to leave this well alone at this point. So I could ramble on with this stuff for hours and hours and hours. There's so much stuff that I've seen I could talk about around what I've seen in industry, but you know, these episodes would just get far too long. So hopefully what I've been through there's shed a little bit more light on carbide. It's shown a bit of industrial experience applied to the home shop. I hope you found at least some of that useful, and hopefully more than anything you're less frightened to go and look on the internet or pick a book up and look at the coding system that is on carbide inserts, because it's not scary. It's not difficult to understand once you break it down into small bits. So yeah, go and have a look. If you've any questions, pop me a question and I'll try and answer it. As I say, I hope you found that useful, and we will catch you all very soon on another video when we'll be making something else.